Okay, today we are going to be talking about the Fourier series, and we are going to establish the equations that allow us to construct all the Fourier series for any function. Okay, so you must know that on a previous video we have introduced the concept of orthogonality in functions, and we also spoke about orthonormal sets that are made of scalar functions. Okay, so in the case of Fourier series, we will be interested in a particular set of orthogonal functions that is going to be made of the next functions. We are going to have a set that will be made of the next. For the first term, we are going to have 1, and then we are going to have an infinite amount of cosines. And the first one will have the structure cosine of pi x over p. Okay, and well, as you saw on that previous video, we were talking about orthogonality in some given interval. Okay, in this case, looking that we are dividing pi x over p, well, we will be talking about that this set is orthonormal in the interval minus p comma p. Okay, perfect. So the next term of the set will be cosine of 2 pi x over p, then cosine of 3 pi x over p, and then we keep going to the infinite. And then we start with, now instead of the cosine, we are going to use the sine. And the first term, of course, is going to be sine of pi x over p. The next one is sine of 2 pi x over p, and so on. Okay? So we have an infinite orthonormal set that is made of cosines and sines, and a constant, which is represented just by the number 1. Okay, where the arguments of the cosine and the sine, well, is just a multiple of the quantity pi x over p. Okay, so this is going to be the set that will allow us to construct the Fourier series. Okay, so what we are going to use to prove that is that, well, we are going to take, for example, the integral from negative pi to pi of two elements of this set, like the inner product we introduced on that video, and we need to establish that for two functions in the form of cosine, for example, cosine of n pi x over p times the cosine of n pi x over p dx, well, this inner product is going to be 0 if n is different from m, and is going to be equal to p if n is equal to m. Okay, this means that, well, these are elements that are orthogonal in the set. And, well, this is the first formula that we are going to use. The next one is going to be the inner product between two functions that are sines. The sine of n pi x over p with the sine of m pi x over p dx. Well, it's going to be the same as the cosine. We will have 0 if n is different from m, and p if n is equal to m. Okay? In other cases where, for example, we have the inner product between the cosine and the sine, we will always get 0. And in the case we have an inner product, for example, of the cosine with the 1, or a sine with this 1, well, it's also going to be 0. Remember that, well, to have something different from 0 in the inner product, we need that the two functions will be equal. Okay, so that's why, for example, in this case where we have p different from 0, well, it's in the case where we have the same function of, for example, sine n pi x over p times sine n pi x over p. But if n is different from m, we have two different functions, so that is 0. It's just like the orthogonality condition. Perfect. So We saw on that video that if we have a scalar function and we have a set of orthonormal functions, well, it is possible to establish that that function can be represented with a linear combination of orthogonal functions that compose this set. So that means that we can establish that any function f of x can be written as a linear combination of the functions that make this set. So for example, for the first term, we are going to have a constant times the first function, which is the number 1, okay? And then we are going to have the sum from n equals 0 up to infinity of some constant, let's call that constant a sub n, and that will multiply all the cosines that we have on the set. Okay, so with this sum, what we want to express is that, well, this is an infinite linear combination of cosines. Okay, so it's an infinite linear combination of elements of this set. And it will happen the same with the sines. Okay, we will have here the sum from n equals 0 up to infinity of b sub n sine of n pi x over p. Perfect. Okay, so this is known as the Fourier series, but actually for convenience, you will see that in most of the texts, you will find that this a0 is dividing, well, it has a 2 dividing here. Okay, perfect. So what we are interested in right now is to find what are these constants a sub 0, a sub n, and b sub n. Okay, we know that we can express this f in terms of this sum, but we do not know what is a and b. So that is what we are going to do in this lesson. Perfect. Okay, so we are going to start by finding a sub 0. Okay, so to do that, well, let's first take the integral from negative p to p on both sides of this equation. What are we going to get? Well, in the first step, we are going to get that this is the integral from negative p to p of f of x dx equal to the integral from negative p to p of a0 over 2 dx plus the integral from negative p to p of the sum from n equals 0 up to infinity of a sub n cosine of n pi x over p dx plus the integral from negative p to p of the sum from n equals 0 to infinity of b sub n sine of n pi x over p dx. Okay, perfect. Looking that, well, this integral depends on x and the sum is over n. And that, well, for now we will not be talking about convergence, but we are going to suppose that these sums converge. We are going to take out the sums from the integral and the constants a sub n and b sub n, just to see more clear what is about to happen. So we are going to have that the integral from negative p to p of f of x dx is equal to the integral from negative p to p of a0 over 2 dx plus the sum from n equals 0 to infinity of a sub n, the integral from negative p to p of cosine of n pi x over p dx plus the sum from n equals 0 to infinity b sub n, the integral from negative p to p of sine n pi x over p dx. Perfect. Okay, first of all, here we have a cosine that we can see that is multiplying 1 here, but we said that, well, these two functions, the 1 and the cosine, are orthogonal. So that means that if we take the inner product between those functions, we are just going to get 0. Okay, that is what we mentioned at the beginning of the video. And here, well, we can say the same argument. We have a 1 here. This is orthogonal to the sine. But we can look this in a different way. Remember that the sine, well, is an odd function, so the sine has a graphic like this. Okay, so if you integrate this on a symmetric interval from negative p to p, for example, well, we are going to have that the integral, looking that is the area under the curve, we'll see that this quantity plus this quantity is going to be cancelled, so the integral is just going to be 0, looking that we are integrating on a symmetric interval. So that means that also this obviously is going to be 0. So we get that the integral from negative p to p of f of x dx is equal to, well, a0 over 2, and well, the integral of dx from negative p to p is just going to be 2p. Of course, we cancel these 2's to get that this is a0p. So remember that we wanted to find a0, so that means that, well, a0 is just going to be 1 over p times the integral from negative p to p of f of x dx. And this is the first important result of the video. Is one of the three Euler-Fourier equations. So we have just found the first constant of the Fourier series. Okay, perfect. So to be able to find a sub n and b sub n, well, again, we are going to take advantage of the notion of orthogonality. So what we are going to do is to multiply, for example, every term of this equation by the cosine, and then take the integral, and we will see that, for example, the sine times the cosine integrated on the interval that will be 0, so this term will be cancelled. This term will survive, but only when n is equal to m, and this term will be cancelled due to the orthogonality. So that is what we want to do to find a sub n and b sub n. So let me rewrite this expression again to do that. Okay, perfect. So now here's the expression for the Fourier series again. Like I said, we are going to multiply first by the cosine of mx pi over p. So that will give f of x times cosine of m pi x over p. It will be equal to a0 over 2 times the cosine of m pi x over p, plus the sum from n equals 0 to infinity of a sub n cosine of m pi x over p cosine of m pi x over p. We can just take this into the sum because we do not have the n index, so that is not a problem. So then we have plus the sum from n equals 0 to infinity of b sub n sine of n pi x over p, cosine of m pi x over p. And then we proceed to take the integral on every term of this equation as the next. Okay, perfect. So that is what we get if we take the integral on every term of the equation. Again, let's see, for example, this term that we have here, and I just already took the sum out of the integral. Perfect. So looking that we have the inner product of orthogonal functions and that are different, this is equal to 0. And that happens again in this term, looking that, well, we have a constant times the cosine, so this means that this is equal to 0. And again, in this term, well, remember, this integral is going to be equal to 0 if n is different from m, but it will be equal to p if m is equal to n. So that means that this is just going to be a sub m p. Okay, so we have that a sub m p is equal to the integral from negative p to p of f of x cosine of m pi x over p dx. In general, we use the n to define this equation, but that is not a problem. We can just switch the m by the n to get that a sub n is equal to 1 over p times the integral from negative p to p of f of x cosine of n pi x over p dx. Perfect. So this is the second important result, the way to find a sub n in the Fourier series. Okay, let me write again the Fourier series definition just to find b sub n. Perfect. Again, we begin with the Fourier series definition, and now, well, it's very obvious, like that we are going to do is to multiply now every term of this equation by the sine function. So we are going to get that f of x times sine of m pi x over p. It will be equal to a0 to sine of m pi x over p plus, well, the sum from n equals 0 to infinity of a sub n cosine of n pi x over p sine of m pi x over p, and then plus the sum from n equals 0 to infinity b sub n sine of n pi x over p sine of m pi x over p. And again, we are going to take the integral from negative p to p dx. Okay, here the integral from negative p to p. Well, let me write it again. Okay, this is what we get. Now we are taking the integral from negative p to p for every term of the Fourier series equation, and I already took the sums out again. So look that we have a very similar situation as we had before. Here we have the inner product between a cosine and a sine, so it doesn't matter the value of n and m, this is always going to be 0. Again, a constant with the sine, the inner product will be 0, and this inner product of sines, it will be equal to p just when n is equal to m. Okay, so that means that the integral from negative p to p of f of x sine of m pi x over p dx is equal to, well, b sub m times p. Perfect. Again, switching the m by the n, we are going to get that b sub n is equal to 1 over p, the integral from negative p to p of f of x sine of m pi x over p dx. Perfect. So this is the third Euler-Fourier equation to build the Fourier series. Okay, perfect. So what I'm going to do now is just to build the Fourier series, but instead of writing a sub n and b sub n, I'm going to take these definitions that we just found just to show you what is the final result for the Fourier series. Okay, so this will be the final equation just by substituting the definitions we found for a sub n and b sub n. We have that a function f of x is equal to 1/2 the integral from negative p to p of f of x dx plus the sum from n equals 0 to infinity of the cosine of n pi x over p all over p times the integral from negative p to p of f of x cosine of n pi x over p dx, and then just plus the sum from n equals 0 to infinity of the sine of n pi x over p times the integral from negative p to p of f of x sine of n pi x over p dx. This is like the explicit form of the Fourier series in terms of the a sub n, b sub n, and a0 term. Okay, perfect. So this is the final result of the video.